Good morning.
Uh, Now we have the first speaker of this forenoon session. As we all of know that the major topics covered under this conference were from inorganic chemistry, organic chemistry, analytical chemistry, physical chemistry, pharmaceutical chemistry, medicinal chemistry, chemical engineering, environmental chemistry, material chemistry, industrial chemistry, and allied subject matters. So in this I have received 300 plus registrations for this virtual mega event, and 100% and 100 plus abstracts have been submitted from all over the India, including China, South Korea, and Algeria. So introducing with you with the first chief spokesperson of our conference, we have the king of chemistry, I would say the king of chemistry, Professor J.D. Yadav, sir, the president of Indian Chemical Society. Regarding his introduction, I would like to say Professor J.D. Yadav is one of the top most highly prolific and accomplished engineering scientists in India. He is internationally recognized by many prestigious and rare awards as academician, researcher, innovator, including his seminal contributions to education, research, and innovation, engineering, catalysis, chemical green technologies. For 10 and a half years, he served as founding Vice-Chancellor and R.T. Mody Distinguished Professor and Tata Chemicals Darbari Seth Distinguished Professor of Leadership and Innovation at the Institute of Chemical Technology, Mumbai, which is a deemed to be university having elite status and center of excellence given by State Assembly on par with IITs, IISc, IIScRS. He currently holds the title of Emeritus Professor of Eminence and J.C. Bose National Fellow in ICT. He serves as the Adjunct Professor at University of Canada, RMIT University, Melbourne, Australia, and Conjoint Professor, University of Newcastle, Australia. He was conferred Padma Shri, the four highest civilian honor by President of India in 2016 for his outstanding contributions to science and engineering. He has been recipient of 2 honorary doctorates, DSc and Doctorate of Engineering. As the Vice Chancellor, he created many records. Now, under his dynamic leadership, ICT had made phenomenal progress, having been declared as Category 1 institute, having started 23 new academic programs, 5 new departments, several centers of excellence, and establishment of 2 off-campuses in Bhubaneswar, with total support of IOCL and Marathwada, with total support of Govt of Maharashtra, and collected phenomenal funds. The ICT is listed in top 100 institutes in the developing world by Times Higher Education Ranking in 2019. He has personally won national and international honors, awards, fellowships, editorships, and several lifetime achievements awards by prestigious industrial organizations. He is an elected fellow of Indian National Science Academy, Indian Academy of Sciences, National Academy of Sciences, India, Indian National Academy of Engineering, as well as the World Academy of Sciences, TWAS. He is a fellow of Royal Society of Chemistry UK, Institution of Chemical Engineers UK, Indian Institute of Chemical Engineers, Indian Chemical Society, and Indian Society for Technical Education, among others. His research productivity is phenomenal with supervision of 100 doctoral and 115 master's theses, which is the first record in ICT and for any engineering professor in India. Besides, he has supervised 37 postdoctoral fellows, several summer fellows, and research staff. He has published 446 original research papers, 115 national and PCT patents, 7 out of which 70 are granted. 3 books. He has possesses an H index of 57, of 265, and having 12,000 plus citations in journals, patents, books, monographs. He is still actively involved in guiding doctoral students, patenting, publishing, consulting, and transferring technologies to industry. The American Chemical Society published a special issue of Industrial and Engineering Chemistry Research in 2014 in his honor with 65 original research papers from scientists from all over the world. He is the founder president of ACS India International Chapter. He is on editorial boards ACS Sustainable Chemistry and Engineering, Green Chemistry, Applied Catalysis A General, Journal of Molecular Catalysis A, Chemistry, Catalysis Communication, International Journal of Chemical Reactor Engineering, Clean Technologies and Environmental Policy, Current Catalysis, etc. He is the founding editor-in-chief of Catalysis in Green Chemistry and Engineering, 2017, USA. He has been a member or chaired several national and international committees of MHRD, DST, DBT, UGC, AICT, CSIR, and PSAs on green chemistry. The Planning Commission's Plan India S&T Committee and the Government of Maharashtra's Rajiv Gandhi S&T Commission Peers Group. He was Chairman, Research Council, CSIR, CSM, member of RC of AICT, and NIIT Trivandrum. He has served as chairman, member of the selection committees of directors of many CSIR labs. He serves as independent renowned public limited companies, Aarti's Industries Limited, Godrej Industries Limited, Megmani Organics Limited, and Bulgaria Chemicals Limited, and one private limited company is Clean Science and Technology Private Limited. He is also a member of FX Council of Indian Oil R&D Expert Advisory Committee ONGC, Energy Center OEC, Glycon Board on Process Safety and the Governing Council DBT Indian Oil Energy Center and member of the DBT Pan IIT Center for Bioenergy. He is chairman of PST's National Expert Advisory Committee on Innovation, Incubation and Technology Enterprise, member of Advisory and Screening Committee of the Common Research and Technology Development Hubs of DSIR, chairman PAC of International Programs in Chemical Sciences and Engineering, TST, and chairman Expert Committee Waste Management Technology, DST. He had the honor of addressing 3 convocations of renowned universities. He is fond of literature, etymology, and Sanskrit. The ICT's university song is written by him. There are 47 video clips, including documentaries on his life on duty. Now, I would like Professor G.D. Yadav to kindly start his session and what we talk.
Thank you, Dr. Nasib Singh. As my opening slide says, I'm going to talk about catalytic selectivity engineering in valorization of biomass, carbon dioxide, and water into chemicals, materials, and energy. So first of all, because I'm the president of Indian Chemical Society, I would like to bring to your kind attention what new things we have started this year. The most important thing is the Elsevier publishers will publish the Journal of Indian Chemical Society from 2021. This was established by Acharya Prafulla Chandra Ray, as you are aware, and this will have International Advisory Board. And I'm appointed as the editor-in-chief, so, and they will be all handled by, Elsevier. New guidelines have been provided for fellowships, life memberships, student membership, institutional memberships like colleges like yours, corporate memberships, and we are also publishing a bulletin called Chemical Water. In fact, on 2nd and 3rd August, Acharya PC Ray's 159th birth centenary celebrations will start. There will be 2 days program and it is open and you can join this program. We have also a new website and started collaboration with American Chemical Society and Royal Society of Chemistry. So this is the, recent advances in chemistry and material sciences. Perhaps you know that Acharya P.C. Ray's was the one who started manufacturing hydroxychloroquine, which is in the news recently. So this you can join, and these are on several dates, 8th, 15th, 22nd, and 29th in the afternoon. So what is today's change, challenge, and opportunity? If you look at this butterfly, you will see that it is changing its colors depending on circumstances. So can we learn something from this butterfly? Or for that matter, if you are living in a crowded place like this fish in this crowded bowl, you have to jump out of it. That means that is the only way you can make progress. Otherwise, you will be one of those many. And at the same time, you have to take risks. You have to jump, you have to take risk. And unless you take risk in life, you cannot do anything. So what is happening today is, never before have so many compelling technological problems have occupied positions of prominence in our system of values. Every moment something happens unexpectedly. Nobody would have imagined last year that we would have locked down and we'll be going into the new way of life. And so posing a new challenge. Coronavirus changed everything. The way we think, live, meet, and behave or rejoice. Constantly on our minds is the fear of the unknown and the uncertain future in every activity. A tiny creature, if you may, has held the world to the ransom with devastating effects. So what are the new words or daily words we find? These are the buzzwords, and they start with energy, water, food, affordable healthcare, and the environment. These are constantly being discussed in newspapers, whether vernacular or otherwise. Then add to this, you have carbon footprint, industry and infrastructure, sustainable development, and GDP. Everywhere we talk about GDP. And all these are affected by this COVID-19. So our economy is greatly affected. So what do we learn from this? Now I'm going to ask you a simple question. How did you begin your day today? And some of these things which are shown in this in the slide are familiar to you. That means you cannot begin your life without some form of the chemical. Or perhaps when you got up, you picked up your mobile phone and looked at it, what was there on the WhatsApp. And that means there is an instant communication also which you are trying to get. And look at this. And what is the motto of the Olympic moment? And why so many records are broken every Olympic? Think of the equipment and attire of players, the synthetic materials and turfs, and all that is required to organize an Olympic. So look at this. These are familiar figures in Olympic movement, and they broke record. Why did they break those records, and how was it possible over the years? So the Olympic motto is CTS, RTS, and FTWAS. That is faster, higher, and stronger. You cannot achieve any of these things unless you have materials which are lighter, which have less friction against air when they run. In other words, or you create the surface of the fabric in such a way, you may have colors of different kind, you always feel comfortable. In other words, name of the various products which are used in Olympics. Synthetic materials and polymers, synthetic textiles. They use drugs and pharmaceuticals. Sometimes the drugs may be bad, but general. The colors and the pigments, the perfumes and flavors, the rubbers and elastomers, the inorganic chemicals, all sorts of gadgets which are used in Olympics, whether they are computers or the mobile phones or air purifiers, sanitizers, use internet, the sensors, the food, the packaging, the pure water and beverages, shoes and rackets and balls and goggles and lubricants, name it. Everything is made from chemicals. So there are synthetic materials which are chemicals, but none of you will give credit to chemistry or chemical sciences, or for that matter, chemical industry. So can you show any three man-made materials or products without the use of chemicals? And why I'm saying this, you look at this simple office picture and what they are using, right from the chairs and the computers and the tables and whatnot. Or for that matter, any house which you may have a house of a different kind. There is a prize of 100 million pounds sterling for anybody, which has been announced in 2008, to name three man-made materials or products which do not use chemicals. And the answer is simply no. You cannot find any. So this prize is remaining unclaimed. So I told my friends in industry, let us announce the prize of 100 crore rupees in India and let anybody come, smart person, and take that prize. You don't have to have that money in your bank because nobody is going to have it. So let me divert my attention to sustainable development in this concern. This is of the UNDP. The first goal says no poverty, zero hunger, good health and well-being, quality education, gender equality, clean water and sanitation, affordable clean energy, decent work and economic growth, industry, innovation and infrastructure, reduce inequalities, sustainable cities and communities, personal consumption, responsible consumption and production, climate action, life below water, life on land, peace, justice, and strong institutions, and partnership for achieving these goals. I can group these SDGs into three. Look at this: no poverty and zero hunger. Is it going to happen in near future? And we're supposed to do it by 2030. Can we do it without chemicals, synthetic chemicals, fertilizers, pesticides? So, or for that matter, use of biotechnology, genetically modified food. You cannot do it. So the other group will have clean water and sanitation. Everybody needs clean water. Or affordable clean energy, because we want to have less carbon footprint. The climate action, think of the Paris Accord or Paris Agreement. Life below water, because many times it is pointed out that a lot of plastic is lying there. Use on land and many others. So in other words, this is possible only by intervention of science and technology, and particularly chemical sciences, engineering and technology. So this is where I would like to tell you, which you may be known to you, but I'm going to give you some different aspects. That is the invention, design, application of chemical products and processes to reduce or to eliminate the use and generation of hazardous substances. So you will question, is green chemistry a new subject? As it is pointed out by many Americans who claim that the father of green chemistry, answer is simply no. Look at this Lee-Blanc process for soda ash introduced in 1791. This was a reaction of sodium chloride with sulfuric acid, and then coke was mixed with that. You get sodium sulfide, and then you treat with calcium carbonate, and you get soda ash, because literally it was an ash. So the name soda ash comes from this ash. What happens in this reaction? You have HCl coming out this, then carbon dioxide, and also when carbon sulfide is produced here, it reacts with HCl. By accidentally, you get H2O. There's a foul smell. In other words, this is a highly polluting process. And that time, there was no restriction on environmental pollution. So HCl used to go in atmosphere because HCl had no use during that time. This is a typical plant in Glasgow. So what happened? That is the time this Solvay process in 1860s was introduced as a substitute for this Lee-Blanc process. And who introduced it? Her Majesty, the Queen's Inspector of Alkalis, George Davis. So George Davis adopted this, and that time the environmental pollution was, gone down. In fact, this is the beginning of green chemistry. But the fellows would not give credit to this. Actually, this is also the beginning of chemical engineering. So the so-called 12 principles of green chemistry, the first one is the prevention, then atom economy, less hazardous synthesis, designing safer chemicals, use of safer solvents, design for energy efficiency, use of renewable feedstock, reduce derivative, catalysis, design for degradation, real-time analysis, and inherently safer chemistry. In fact, why 12? You will ask this question. Because there were 12 nasty green, nasty chemicals, which were all containing chlorine, and they were all pesticides. So here, if we have atom economy, catalysis, and renewable resources, that is what all matters. In other words, for instance, the energy efficiency. In previous times, sulfuric acid manufacture it generates a lot of heat. So now sulfuric acid plant is taken as an energy plant where incidentally sulfuric acid is produced. The same is the case with ammonia plant. So green chemistry principles first were adopted by inorganic chemistry, much later by the organic chemistry. And so we can see that, so this is what happens. So the Solvay process of 1865 was the genesis of green chemistry and engineering. And I wrote an article on this, giving the history behind this. It's a simple reaction of sodium chloride and calcium carbonate, but this reaction does not proceed unless you use ammonia. And there was no synthetic ammonia available that time. So you can imagine the geniusness of Solvay, unnamed Solvay. Anyway, so in today's world, as I was telling you about the Olympic movement, we need materials and we need to use smart chemistry. So what are these materials? Well, the regular materials, whether you want to reduce the density, make them tough, all that thing. So we know that the plastic has become thinner and thinner and tougher. So you have functional materials. You introduce functionality in the material, and you have the smart materials. They can wink, they can smile, they can laugh. This is creation of chemistry and above all the engineering materials. In other words, material chemistry cannot be improved without contribution of chemistry. This is very important. So what is the beauty and charm of chemistry? The attributes that perhaps most distinguishes chemistry from the rest of the sciences is the ability of chemists to control the structure of matter at the molecular level, from complex natural products like vancomycin to nanoparticles and whole genomes. So you can imagine, so there is the boundary between chemistry and biology has disappeared, as your Vice-Chancellor was saying. So biology all follows laws of chemistry. The cells follow laws of chemistry. So chemistry is increasingly shifting from structure to function. And chemists will need to develop better strategies to efficiently generate molecules and systems of molecules with desired physical, chemical, or biological properties in order to meet the biomedical, energy, and environmental needs of the future. And this is very much so right now. So I'm going to show this simple photograph here. This I have displayed in my institute as well. What are the contributions of chemical and allied industry to modern society? Be that fuels, energy, materials, basic needs, luxury, comfort, of quality of life. And now we are talking about Atmanirbhar Bharat. You start on the left side, they are all simple raw materials, maybe natural gas, or maybe crude oil, or maybe coal, or whatever, and air, and the sulfur. And you can make all these commodity chemicals, then the secondary commodity chemicals, then the intermediates, and finally you make all these finished products which the normal public sees, whether they're textiles, safe food supply, transportation, housing, recreation, communication, and the communication has to be instant. You are not going to wait for anything. So like you every now and then you look at your mobile phone. And health and hygiene. All these are, and you imagine in this 70% of these chemicals never are sold off the shelf. In other words, chemicals like this are never seen. We just enjoy the end product. So this is very, very important to show to the students of chemistry how we contribute to the quality of life, so-called luxury, comfort, and longevity. So all these chemicals, in fact, we import a lot of, small molecules, intermediates, and APIs from China. Almost 80% of APIs are imported from China. Why not make them in India? And this is where our Honorable Prime Minister is talking about Atmanirbhar Bharat. And my personal belief is that chemistry will have a great role to play. So in the same way, I must tell you the importance of catalysis and continuous operation. We deal with about 100, a million to 100 million tons per annum production capacity in refinery, by 2 orders of magnitude less in bulk organic chemicals, further reduced by 2 orders of magnitude in intermediate and fine chemicals, or in pharmaceuticals, 10 tons or something like 1,000 tons. But look at the byproduct formation per kg of the product. It is the minimum in petroleum refinery. Everything is used in that. And why? There, the role of catalysis is maximum, and these are all continuous processes, and therefore they are safe. So we go down, we'll find the byproduct formation increases depending on the fineness of the chemical. So bulk organic are the intermediate and dyes and pharmaceutical. And see the role of catalysis, it goes on diminishing. And at the same time, the number of operations, the number of reactors and separators. If you have one reactor, there is at least one separator, sometimes more than 2-3 separators. And you will see that all these processes on the pharmaceutical and all, very few processes are continuous processes, and they're hazardous. For example, they may use lithium-based chemistry, or they may use Grignard or Grignard reaction, which are highly hazardous. And they are all, or nitration reaction for that matter. They are all batch processes. Several times they are highly dangerous. So my advice is make them continuous processes, use microreactors and separators of that kind. So let me switch gears and go to the primary energy consumption of the world. And this is what we are all concerned about. And you will see that the BP Energy Outlook every year is published in June. And you can see that by 2040, you will see that we have oil, gas, coal, nuclear energy, hydroelectric, and renewable resources. The contribution by all these components of primary energy will increase. And you will see that the renewable and all, this is all these is, and what is happening? Because of this consumption, carbon dioxide in gigatons of CO2, you see that how they are also increasing. So this is, as we go along, as we advance, by 2030, we'll have huge number. Because more energy is required, our gigatons of carbon dioxide going in the atmosphere is increasing. So in this particular case, you look at the end user sector, where it is being used. So transportation section, industry, non-combustible, or buildings. And you will find that most of the time we talk about transport and we never talk about our industry, but we never talk about building. Believe me, buildings consume a lot of energy. And the major components, OECD nations, China, India, other Asian nations, and Africa. And you see once again the type of fuel, how it is growing. So oil will still continue to be used. New gas reserves will be found, so it will be used. And then you say coal will still continue to be used. And although people are saying coal will be banned, that is not correct. The projections are that coal-based economy, where coal is converted into alkenes, or you can directly convert to methanol. All those things are going to be there. And nuclear energy share, because nuclear energy is the safest form of energy. And so you can see that share will be increased. And renewables will slowly increase to that extent. So this is driven by the prosperity in our country as well as China. You can see the GDP will be increasing, and you see the trillion US dollars PPP, and you see the global GDP growth. And typically this growth is supposed to be 3.5%. And anybody who breaks that barrier, like India and China, is supposed to do, in fact, some of the application nations as well. So we see that if the growth is beyond this 3.5%, you are a comfortable region. So at the same time, because of higher living standards, the energy demand increases and substantial gain. So you can see that the GDP, if it grows to beyond something like 3.5, I said, if it goes to 5, you can imagine a billion tons oil equivalent, what is required for that. So at the same time, something called as the standard of living of one is the best. majority of the countries are less than 0.8. That means standard of living has to increase daily. So in fact, that is also related to the demand in energy. So the global energy faces dual challenge. That is the need for more energy and less carbon. So we must have less dependence on the carbon. So you see the more energy, if you increase more energy, carbon has to be increased. So that carbon dioxide will be increasing. Therefore, we need technology where carbon neutral or less carbon, that means less CO2 technologies are required. And this is where I'm going to talk about my own research and others. So this, the non-combustion demand, you can see by 2040, the oil demand is still there. And by 2056, there will not be any oil remaining. So we have to have, at the same time, there will be ban on some plastics. So there is a reduction in that particular demand. So we see that the increasing environmental concerns and ban on single-use plastics, this is shown in this particular scene. And we see that this between 2020 and 2045, you can see that the total energy demand will increase. So buildings account for almost 33% of the energy. So this is normally not talked about, but buildings contribute a lot to this global, pollution. So we can see, so we have carbon capture and utilization and storage, our circular economy. This is where we see that once again, between the year 2017 to 2040, we have to look at this particular economy. So the energy scenario tells us that the solar energy will be increased. India is the, in the chair of the Global Solar Alliance. And wind, then you have nuclear energy in between oil, gas, and all these things are telling us that energy demand. So you see globe, and this is the hydroelectric and solar. So the Paris Treaty or Paris Accord, why it was signed, it is bound at about 0.10 degrees Celsius rise per decade. So 0.013 per year. And that is having disastrous effect on the climate. So let us look at this. So that means we have two sources of carbon, that is the non-renewable carbon in the form of oil, natural gas, and coal, and the renewable carbon in the form of biomass. So we have many well-known technology here, that is gas to liquid, or coal to liquid, or coal to gas. And here on renewable carbon, the biomass can be chemically converted, biochemically converted, or thermochemically converted. So in this particular case, there is a direct chemical conversion of biomass. Here it could be fermentation, or you may have enzymatic processes, or biomass to gas, or biomass to liquids. These are well-known technologies. So what it means, whether the carbon is coming from fossil fuels or biofuels, there is a need to convert the carbon dioxide into fuels, chemicals, and materials. That is the theme of my talk. Hydrogen is the cleanest fuel, which can be produced from hydrocarbons or from water and can be used to convert CO2 into useful products and the treatment of biomass, whether virgin or waste, into hydrocarbons with the help of novel catalysts. Hydrocarbons can also be reformed into hydrogen, but still carbon monoxide and or carbon dioxide needs to be utilized. So whether you talk about the petroleum-based economy or the bio-based economy, ultimately carbon dioxide is coming out. So here you can see the CO2 is echoing. So it has to be valorized into something. So you see here that from year 2000 going up to 2020 to 50, the CO2 concentration in the atmosphere will increase from something like 410 now to something like 2000. That will be really disaster. So, and what will be the temperature rise? This will be anywhere between 6 degrees to 8 degrees C. So, in other words, carbon dioxide has to be properly utilized. So either we convert that into products, or you capture it and store for future use, or carbon dioxide again converted into some form of materials or chemicals. So now let us compare the fossil energy carriers and the biomass. So in the biomass we have cereals, grass, wood, and oil plants. And in there we have crude oil, natural gas, and coal. So these are the normal BTX processes and the syngas, and we can make all these platform chemicals. Nasib, can you just see that other microphones are muted?
Sir, I'm trying here. I don't know who is.
Okay. So you can see, so you have these precursors from biomass like sugar, polysaccharides, which contain cellulose, hemicellulose, starch, and lignocellulose, or lignin and oils and proteins. And you get these platform chemicals and finally all these materials. So what it means, the carbon dioxide refinery of the future, whether you have photosynthesis to into oxygenates, or you react with hydrogen to get hydrocarbons, and you refine and make chemicals and so methanol, dimethyl ether, and formic acid can be easily formed in carbon dioxide. Oh, somebody's kid is ready. Please, will you please mute your microphone, please? Please mute your microphone. So what it means, we require better catalytic materials for conversion of carbon-based feedstock. Waste minimization and process intensifications are required. Then we must have renewable sources of energy. And the best one, carbon neutral, is hydrogen as the source of energy. And let me compare some of these statistics. Indian oil import last year was 228.6 trillion tons of crude oil. And our government wants to reduce the import of oil by developing new technologies and the renewable resources, whether solar, wind, hydro, coal, and fuels, and chemicals, or for that matter, the 2G ethanol and biodiesel. So India's share of total global primary energy demand is said to be roughly double by about 11% by 2040, which is underpinned by strong population growth and economic development. So India accounts for more than a quarter of net global primary energy demand between 2017 and 40. 40% of this, 42% of this new energy demand is met through coal, meaning more carbon dioxide emissions, and which will be doubled. And gas production grows but fails to keep pace with demand, implying significant growth in imports. So India's energy requirement is 156% primary energy consumption, 11% of the global energy by 2040, 58% share of coal in India's power generation mix, and 116% growth in India's CO2 emissions. So we have signed the CO2, the Paris Accord. So this is where the renewable energy consumption will surge from about 20 million tons of oil equivalent today to 300 million ton of oil equivalent. This is huge, the demand, which will be concentrated in the power sector and driven largely by growth in solar capacity. Despite this growth in renewables, coal continues to dominate India's power generation mix, accounting for 80%. So this is where my research comes into picture. No carbon-based fuels and hydrogen as source of energy. So why hydrogen? Because it is a cleanest fuel, and I personally believe India should adopt the hydrogen economy, and that should be their goal by 2030. It produces no flames, high combustion temperature, extremely low boiling temperature, lightest weight, does not easily spontaneously combust, and it is colorless and odorless. So we develop a technology with the help of ONGC for hydrogen production. And this has a huge potential to generate hydrogen at about 95 cents without valorization of co-product oxygen. This hydrogen will be useful for the hydrogen economy, including ammonia synthesis, hydrogen fuel cells, electricity generation, and e-vehicles. It is also coupled with solar energy through molten salts. So in other words, utilization of carbon dioxide, water, and catalysis will lead to sustainability. So as I told you, this is a hydrogen production from water. There is no carbons in the feedstock. So it is, again, the importance of materials in this particular technology came to the fore. So once again, we must have better catalytic materials. So what we did, I'm looking at some fundamental studies which we did on pore structure while developing new catalytic processes or green chemistry. So the pore structure is inseparable from convecting, diffusion, and interfacial effects that occur within the pore. And they are related. So you can discuss coal, rock, soil, membrane, catalyst, buildings, roads, cells, skin, eye, etc. And they are zigzag and zillions of pores interconnected. And the interconnectivity matters. And in that interconnectivity, we have a role of surfaces, interfaces, and remember, only connected pores matter. And so the network in the cities is just can be treated by the network of these pores. So we have this network of fluids as well. So this is a simple picture, and I can model it by using percolation processes. I can look at the products and reactants, how they're going in and how they're coming in. So there is a continuous pore network providing very high surface area and uniform or non-uniform pore sizes. The surface properties of the pore net are tuned by surface modification, and the particles, including nanoparticles, has to be dispersed. So in another concept which we propose is the so-called cascade engineered catalytic reactor concept. Instead of many equipment, you can reduce the number of equipment, that is number of reactors and number of separators. You have the same type of catalyst. And there are many reactions in industry where they do condensation followed by hydrogenation, and same reactor can be used. So this is the concept. So similar kind of concepts we can use about biomass, and you have to valorize this biomass. So once again, the role of catalyst and their pore size and surface properties will matter. So remember, I also mentioned about 2G ethanol. The government of India has a new policy on non-conventional resources. So ethanol blending in petrol will increase to 22.5%. In fact, we don't have that much ethanol. What we produce is only about 3,000 million liters of ethanol per year. And ethanol can increase the RON, research octane number. So what we do, our personal belief, my personal belief as a scientist is that ethanol should not be burned as a fuel, but can be made use as for making other products. So what should we use for fuels? Yes, other renewable resources, including hydrogen and the solar energy and wind energy. So here, what are the bulk chemicals we make from carbohydrates? Like, transportation fuel, vinyl acetate, butadiene, styrene, propylene, ethylene, bagasse, and whatnot. So here are two wings to this. One is the lignocellulose crop and another lignocellulose residues, like the agri-waste which the farmers throw. So these are burned. So here a pre-treatment, you get C5 sugars and lignin and or C6 sugars, and this becomes a source of new materials and energy. And here you can again pre-treatment gasify, or you have syngas, and then you have Fischer-Tropsch synthesis or alcohol synthesis. So in other words, this biomass can be converted. So we have thermal conversion, thermochemical conversion, biochemical conversion, and chemical conversion. All these processes at some stage or the other require a good reactor design, good catalyst, and process intensification. So if you have a best biomass, you have to pre-treat it, bioprocess it, use biocatalysis, and polymerizing. This is one way of doing it. And when you have C5 or C6 sugars, xylose and glucose, you can make a number of products, platform molecules like xylitol, furfural, sorbitol, livininic acid, lactic acid, succinic acid, 3-hydroxypropionic acid, ethanol, ferulic acid. And you can see that all these things can be used for making some products and materials. And this is a complex structure of lignin, and all these oxygen containing compounds can be broken and taken to some new value-added chemicals. So pyrolysis of lignin-based oil can give many, many compounds, right from guaiacol to syringic oil and whatnot. So we did some work in this area, and one of the things was cascade engineered catalysis, which I said. So cascade engineered catalysis, we can have C4-oxopentanoic acid, hydrogenation, we get this 4-hydroxy, this is livinilic acid. Then you take further dehydration, you get ring closure, or this you take further and you react with ethanol and you can get ethyl 4-oxopentanate. All these are very valuable chemicals. So in other words, or you can have hydrogenation of gamma valorolactam, which is again the so-called GVL is a very important chemical. So we can make that particular one. Again, the same, you can see that if you have a catalyst which has a hydrogen activity, hydrogenation activity, and acid centers, you can make this. So this is again a cascade engineered idea which we promoted. So gamma butyl of succinic acid to succinic anhydride, and you can go ultimately to 1-butanol in this particular case. So you imagine these kind of reactions are very complex reactions. So you need to study the kinetics of each stage and design. So this is another aspect. Another aspect which is talked about is the so-called biodiesel. Remember, biodiesel requires the vegetable oil, and you cannot, so it will be better to use vegetable oil. And in this, you always get 10% by weight of glycerol. And unless you valorize glycerol, biodiesel is not sustainable. You have to give subsidy. The government is to give subsidy to make biodiesel popular. So what are those products? You can make acrolein or acrylic acid, 1,3-propanediol, 1,3-propanediol, epichlorohydrin, glycerol carbonate, and glycidol, and these are all bulk chemicals. So glycerol hydrogenation can be done by using all these processes, whether it is esterification, oxidation, chlorination, esterification, oligomerization. They require catalysts, and they require new catalysts. And you can see that the number of products you can make from glycerol, which is a co-product of this biodiesel process. We studied all these reactions, developed many catalyst patents and all. So you can imagine this kind of chemistry. Or you take glycols and 1,2 or 1,3 propylene glycol, you can convert into ethylene glycol, and ethylene glycol becomes building block. So for example, if in HMF is done, HMF is from glucose. So you can take HMF, hydroxymethyl furfural. So you can see that from here, you can make many different polymers or fuels or fine chemicals. So for example, D-fructose to HMF, you can get livinilic acid and formic acid or the ether, and this is the fuel additive. So we did many catalytic processes like synergism of acidic ionic liquid and sulfurone as a modifier. You can see that this is using heteropoly acid. So this is negative ion is a heterocation, and this is what the reaction is. Or you can use micro acid state reaction where fructose, ethanol, and deep eutectic solvents are used, and this EMF is a biofuel. Or you take HMF, which is a platform molecule, and make all these chemicals like caprolactam, 5-alkoxyfurfural, 2,5-furan dicarboxyl acid. This will be the so-called bio polymer. This can be used as a precursor to biopolymer, and this is very, very important. Or you make adipic acid or livinilic acid. We have studied all these reactions in our laboratory. So some of the bulk chemicals we studied: livinilic acid, gamma valolactone, dimethylfuran, and furan dicarboxylic acid. So some processes we use hydrogenation using magnetically separable iron, palladium, and carbon core shell structure, bimetallic catalyst. In another case, we made this pure additive 2,5-dimethylfuran using palladium modified heteropoly acid, which is modified by cesium, and K10 catalyst, which is a clay. So you can see that this is a green process. This we published in Green Chemistry. And so you can see that, or you can use this furfural alcohol, ethoxymethyl furfural, ethyl livinol. This is again ethyl from furfural alcohol. We can do many, many reactions of this kind. Or you have a catalytic condensation of 5-HMA4 modified heteropoly acid. Or sustainable selective synthesis of 2,5-furan dicarboxylic acid by 5-methyl hydroxy furfural using manganese ferrite. So we can produce all sorts of chemicals, we have done a lot of work in that area. But I want to point out towards the end of my presentation is hydrogen production. So look at hydrogen. Why hydrogen? I'm shouting at the top of my voice that compare hydrogen with wood or methane or diesel or gasoline, which is petrol and coal. It has the highest specific energy. So hydrogen is very good. And we can make hydrogen by many, many different parts, like the renewable resources, nuclear energy, or fossil fuels. All of them can be made. And if you look at the analysis of this source, natural gas, wind, uranium, you can see many different. We can do the economic analysis of these processes, whatever we do. So thermochemical, electrolytic, and photolytic processes, these are commercially being used. Of this, natural gas and biomass. So let me take biohydrogen. We have fermentation and biophotolysis. We get 4 different types of hydrogen production technology. And so if you look at the source of hydrogen production, steam reforming of natural gas is most widely used. Almost 48% is steam reforming. That is what industry uses. Or sometimes they're next to either oil or naphtha refinery. Or you have coal gasification. So imagine. And then water electrolysis is very less, about 3.9, and other sources 0.1. That other sources may be hydrogen coming from the so-called caustic soda industry. So here, what it means, you take any carbon and you need to provide heat. You can use nuclear energy and produce hydrogen. So this is one way. And then the next part is the hydrogen storage. You look at the compressed at 5,000 psi and gasoline is 20 liter atmosphere. You see the kind of pressurization is required to reduce the volume. So liquid hydrogen, chemical hydrides, and whatnot. So the hydrogen market is in petroleum recovery, refinery, metal production, fabrication, aerospace, and fuel cells. And the demand for hydrogen is the largest in hydrogen refinery. Then followed by that, ammonia synthesis. Automotive fuel is emerging area with huge potential. And hydrogen fuel cells to generate electricity from oxygen and hydrogen as a high calorific value. So there is something called wells to wheel efficiency of hydrogen vehicle. You can find that in this particular case, hydrogen fuel cells have something like 30% efficiency. And if you look at the grid, it is only 25%. So hydrogen production and next taking it to the fuel cell, we lose lot of efficiency. So in any fuel processing, whether it is gas, liquid, solid fuels for hydrogen production, this is a typical plant. Either you have a solid fuel or a liquid fuel or natural gas, and these are the processes. Okay, and you will see ultimately when you have hydrogen and carbon monoxide, syngas, you can have Fischer-Tropsch or methanol, ethanol, or dimethyl ether, ethanol synthesis, and other high-value products. Or in fact, you can take this to so-called hydrocarbons. So same way, we can convert biomass to hydrogen. So in other words, whenever you use biomass, you have to talk about the carbon only, okay? Because carbon cannot be let go in atmosphere, it has to be. So we also studied biomass-derived alcohols and feedstock, ethanol, butanol, glycerol, and ethanol. These are all renewable resources, different types of catalysts which developed by us, and these are published in and also patented. Okay. So if you look at the reforming, steam reforming is the most widely used. Okay, steam reforming of methanol or methane, and then autothermal reforming and partial oxidation. You can see that these processes are being talked about. In the case of thermochemical water splitting for hydrogen, there are series of chemical reactions at high temperature, like sulfur iodine cycle, cerium chlorine, ionic chlorine, vanadium chlorine, copper chlorine. We studied this as well as this, and we have patents in this copper chlorine cycle. So in the case of solar hydrogen, what it means, you take this carbon dioxide pool and you see water electrolysis. So all these processes in this case or biomass, we can produce hydrogen, and then you go to methanol. Similarly, all these things can be considered. But look at the technology maturity. Steam reforming and partial oxidation are the commercial processes. Biomass gasification is also commercial, or alkaline electrolyzer is also commercial. But the efficiencies range between 50 to 85%. So, in other words, if you look at the maturity of technology, steam reforming, electrolysis, and byproduct hydrogen, these are the many currently developed. And the other where we are doing research, they are in this particular area. So we can compare this various processes depending on the feedstock, natural gas, coal, woody biomass and whatnot. And look at the cost of hydrogen, anywhere between $2.27 per kg to something like 1.48. And you see that all other technologies, sometimes 5.78. And the process which we develop, which is being funded by ONGC and which are going to build a big pilot plant now, this is only 95 cents. So ours is the best process so far as technology is concerned. So what should be the future cost of electrolytic hydrogen? You can see that it says it should be less than $2. Okay, this is the Department of Energy of US. So the DOE projection says, which is central or distributed, coal gasification, high temperature electrolysis, or you have this bio-derived liquids and microbial bioconversion. And the plants do not become commercially viable unless we cross certain capacity. Estimated plant capacity, C per kg per day, 500,000, 5 lakh kg per day. Unless you go for this does not become economical. So in other words, if you look at the solar energy technologies, the photovoltaic, the energy efficiency high, and the complexity increases in this direction. So if you have a low efficiency and the complexity diminishes. So we have a choice between this. So if you look at the profitability of the solar-based, the hydrogen-based economy, we can see that from here to here by 2030 plus, this is going to be a reality. So in other words, we should be prepared for hydrogen economy. So novel catalytic technologies must be used. So you can see that the carbon neutrality we should achieve. So here we see this is 0, so it is going below. So this carbon neutral thing has to be done. So we have to look at the non-CO2 agriculture, tertiary transport, all these things we see. As we go towards 2050, we must go down the million tons equivalent of carbon dioxide equivalent it should be going down from 5,000 tons to less than 0 tons. So this is a tall order for science and technology. So the ideal goal is conveyed. So this is what our efforts are in that direction. So you can see that the so-called zero waste society is a progressive path for linear. So we have to concentrate on this, not the linear economy, and convert that into circular economy. That means nothing is waste. That is the idea. We have to use everything. So in our process, in ICT's process, we have this, see, we have molten salt, we have solar power, copper chlorine cycle, we generate hydrogen, we generate oxygen, and we can treat biomass, waste or virgin, and carbon dioxide. And you see how many products we have 5 patents. We have hydrocarbon, methanol, DMA, formic acid, farmers, syngas, alcohols, and all those things. In other words, this will be a future of carbon neutral or carbon negative technology. So what are the challenges? Nothing is waste but carbon neutral or carbon free processing. Carbon dioxide should be valorized using novel catalytic technology and multi-phase reactors. Systems engineering approach, only useful products and energy, leave the boundary. So in this case, we have waste biomass, plastics, woody biomass, everything. And nature will serve as a guide to develop this process. Carbon dioxide, water, sunlight, and catalysis by chemical or biological species is going to make it possible. So I must thank ONGC Energy Center, and these are my professorship endowment, and also JC Bose National Fellowship of PhD, and this is my group. Thank you very much for providing this opportunity to discuss some of our work and the global scenario. And if anybody has some question, I'll be very happy to answer. Thank you so much.
Thank you so much, sir, for your wonderful and stimulating speech. On behalf of Tron, convener and organizers, I thank you for giving your more precious time to us. We are so much grateful for your useful, knowledgeable big talk. Sir, you are a very great and eminent personality with simple living and high thinking, and having a kind heart, and you are very down to earth. Thank you so much for your support. By all means, for us, your presence as senior most and first speaker is not less than the blessing of Lord Shiva itself. for me in particular. Hopefully, all the attendees will gain much knowledge and they will act boldly on what they done future through their event. Once again, I thank you, sir.
Thank you. It's my pleasure. Thank you so much. And I wish all the best to your conference.
Thank you, sir. Thank you. Now is there any question? Is there any question? Please, if someone asks questions, please.
They can type it. Okay. Thank you. I think there is no question. So I'm leaving. Okay. All the best.
Okay, sir. Thank you so much for your presence.
Thank you. All the best, Nasir.
Thank you, sir. Thank you.